So 5.4, we're going to start with we're going to start taking some of these trig functions from the unit circle, and we're going to start taking them individually. There's 6 of them. We're going to start taking some of them individually and looking at them unwrapped, if you will, off the unit circle onto the coordinate plane, and we're going to see what the graphs look like, and then we're going to come up with these brand new functions. Now, how do we say that word? Sine. Yeah, it's the long I. So it's not sinusoids, it's sinusoid. It's a long I sound. So if you put a bar over the I, sinusoids. There are 2 sinusoids. Can you guess which of the 6 trig functions are going to be classified as sinusoids? Sine and we're going to call one of them sine of theta, and then we're going to call it f of x. No, take a more logical. Don't go far-fetched. Sinusoids. Cosine, because cosine actually has in its name the word what? Sine. Yeah, so that's the other one. We'll call it g of x for now, but it's going to be cosine of x, theta. So those are the only 2 sinusoids. Now, if you remember from what we've been studying so far, these are really the 2 main trig functions, aren't they? When you learned SOHCAHTOA, these were the first 2 that you came across, SOHCAH. We also know that we can express from yesterday every single one of the other 4 trig functions in terms of sine and cosine, right? Cosecant's the reciprocal of sine, secant's the reciprocal of cosine, tangent is sine over cosine, and cotangent is cosine over sine. So this is like the most raw, this is like the DNA. This is the DNA of the trig functions. And then everything else is just a restructuring of the DNA, sine and cosine. So what we're going to do is we're going to, like I said, unwrap them from the unit circle, and we're going to see what they look like. So we're going to start by doing a T-chart. Y'all remember making T-charts in Algebra 1? Or a T-table? Maybe that's more alliterative. A T-table, where you're going to pick values. Let's write our function out here real quickly here. We're going to have f of x equaling sine of x. Now, notice what I did here. I abandoned theta. Theta is now going to equal x. But x represents our angle. X is no longer the horizontal side of the reference triangle. Are you okay with that? We're going to replace theta with x. You can easily write f of theta equals sine of theta, and it still makes sense. But when we talk about functions, we typically use x, so we're not going to abandon that at this point. Okay? So x is now our angle. X is the angle. It's not the horizontal side of the reference triangle. You have to know that, okay? So let's make a T-chart now, or T-table. We got x and sine of x. Let's just go once around the unit circle and see what happens. If I start at 0, what's sine of 0? This could prepare you for tomorrow's quiz. What's sine of 0? No, sine is never D and E, if you remember. Cosine is never D and E. That's another thing that's worth mentioning about these 2. Sine and cosine are never D and E, whereas the other 4 always have at least 2 D and E's on their 6 trig functions. No, what's sine of 0? Sine is the height. When we're on the x-axis, sine height is nothing. It's 0. All right, what's sine of pi 6? Let's do pi 6. I'm going to choose angles judiciously here. So as I start rotating up counterclockwise, what's sine of pi 6? 1/2. Very good. What about sine of pi halves if I rotate all the way up? Let's go ahead and write these as I'm going. Here's sine of 0. Here's sine of pi 6. Here's 0. Yeah, pi halves is straight up here. It's 1. Okay? Let's do 5 pi 6 now. What's sine of 5 pi 6 over here? If sine of pi 6 is 1/2, what should sine of 5 pi 6 be? It's also 1/2, right? It's the same triangle. It's the same reference triangle, and we're above the x-axis. It's 1/2. Okay, let's keep going. What about pi? What's sine of pi? We're back on the x-axis again, so it's 0. Yeah? All right, what would be the next pi 6 angle in quadrant 3? Good, 7 pi 6. What would sine of 7 pi 6 be? Negative 1/2. You got it. You're figuring it out. All right, let's go straight down to 3 pi halves. What's sine of 3 pi halves? Negative 1. Very good. All right, and then over here in quadrant 4, what's the pi 6 angle? Well, what's the angle over there? 11 pi 6, right? 11 pi 6. So what's sine of 11 pi 6? It's negative 1/2 again. And then coming around full circle, 2 pi. What's sine of 2 pi? 0. So let's think about the unit circle. That's what I drew right here. This is still the unit circle. We're talking about the reference triangles as we go. The height of the reference triangle starts at 0. It increases up to a maximum of 1. And then it decreases back down to 0 as we hit pi. And then as we go into quadrant 3, the height of the rectangle again goes to 1/2, up to 1, down to 1/2, and back down to 0, but it's in negative land. Okay? So if you look at the y values here, let's look at the y values, which represent the heights, right? The sine of x represent the height of each of these rectangles. The height increases to 1, decreases back down to 0, decreases to negative 1, and then it increases back up to 0. Y'all see that? Increase, decrease, decrease, increase. Let's go ahead and plot these points on the coordinate plane. So let's give ourselves now the x and y axis. We're not on the unit circle now, we're on the coordinate plane. So we're measuring x, which is the angle in radians, on the x-axis, and on the y-axis, we're measuring the sine of x, the sine ratio, the height, okay? Let's put our points down there. I know it goes up to 1, and it goes down to negative 1. So let's go ahead and label the maximum and the minimum, 1 and negative 1. Let's also come out about right here towards the end of our graph. Leave a little bit of space after that. But go out near the end and put 2 pi. That's one rotation. Okay, now let's cut that in half. On your paper, you can cut that in half. What's half of 2 pi? That's pi. So you can put it like bisect your little interval. Everyone's interval is going to be a little bit different. But if you bisect your interval, you can put pi. Now let's bisect that interval. Cut that interval in half. And what's half of pi? Pi halves, yeah. Now let's do the next interval. Cut it in half. And that would be 3 pi halves. So we have 0, pi halves, pi, 3 pi halves, and 2 pi. Okay. Now, we also have these other angles that I chose. I chose pi 6 right here. And I chose 5 pi 6. I chose 7 pi 6. And I chose 11 pi 6. That's where it's going to equal 1/2. Now, I put those in green because here's what I want to do. I want to plot these numbers first. 0, 1, 0, negative 1, and 0. Let's plot those points first, okay? So I'm going to have 0, 0, pi halves 1, pi goes back down to 0, 3 pi halves is negative 1, and 2 pi comes back to 0. You'll see that? So the y values increase, decrease, decrease, increase. Up, down, down, up. Those represent the height of my reference triangles as I make it once around the unit circle. Now, how do I connect those dots? Do I connect them with straight lines or curves? Curves. Here's how we know we're going to do it with curves. At pi 6, which is just past 0, it's not between, it's not the midpoint, is it, between 0 and pi halves? Pi 6 is not the midpoint of 0 and pi halves. But I already reached the midpoint vertically by the time I get to pi 6. So it's increasing at an increasing rate. Y'all see that? So when I connect the dots, here's what I'm going to do. I'm going to draw it like this, and then it levels off, and then it comes back down like that. Symmetrically. This is going to be symmetrical about the line x equals pi halves. Okay? So if you had like a dotted line running down through here, there should be symmetry across that line. In other words, it increases at the same rate it decreases. Now, also symmetrical is how it continues down to negative 1. So it's going to continue down like this, and then it's going to increase like this. And again, we have symmetry about the line x equals 3 pi halves. So if you were to draw a dotted line there and fold it, it should line up with itself. And those two lobes that we created, one above and one below, those should be equal to each other. This lobe here and this lobe here, although my bottom one seems to be a little bit bigger, the two lobes, the two lobes, we'll call those lobes, are equal in area. That kind of gets into a calculus aspect. We study that in calculus. But it should be perfectly symmetrical. Now that's once around the unit circle. What do you think is going to happen if I continue past 2 pi? It's going to go up again, right? If I make a second rotation around the unit circle, so instead of, let's do 11 pi 6, if I come around here and I'm at 13 pi 6, and then I add 5 pi halves, so on and so forth, aren't I going to land at the exact same spot the next time around the unit circle? And my values are going to be the same, aren't they? And if I go around again, coterminal, I'm going to get the same trig values. And if I go around again, coterminal, I'm going to get the same values. What if I rotate negatively? Will that affect it? If I rotate negatively and I stop at the same place, coterminally, aren't I going to get the same values? Yes. So here's what we could do. Watch this. Take your toolbar that allows you to copy and go ahead and circle what we drew there. Copy it. Let's come over here now and paste it. Paste the start of that new value, in other words, the old origin, paste it right back down at 2 pi. Boom. And then get rid of the y-axis. Okay, and if you want, you can get rid of the names. The angles are different now. Can we do it again? Let's paste it down over here. Put the origin at the end. Boom. Erase the y-axis, and of course erase the angles because the angles are obviously bigger now. So on and so forth. This graph is repeating itself, isn't it? And let's do one in negative land. It's going to interfere with our table, but that's okay. Let's paste the image down, and we'll put the end of the graph, okay, at the start of the next one. And we paste it like that, and then of course you can erase the angles. There you go. So this graph is the graph of f of x equals sine of x. This is the graph of f of x equals sine of x. We call this a periodic function. Why do you think we call it a periodic function? It has the same what? It does the same thing every time. What is the every time? How long does it take for it to do the same thing? What's that? Every rotation, which is how many radians? You're right. Not 2, but 2 pi. Yeah, this graph repeats itself every 2 pi. So here's what a periodic function is. The definition of a periodic function is a graph or a function that repeats at regular intervals. Called the period, which is also known in science as the wavelength. Y'all have heard wavelength before, right? Yeah. So this is a sine wave. So we could also call this a sine wave. These are also called wave functions, okay? Guess what the period p is for this function? It's 2 pi. It's the smallest distance for which this function repeats itself. That's called the period, okay? The period is what is the wavelength. They're interchangeable. In science class, you use wavelength, and you use lambda for that, which is kind of a cool symbol. But in math class, we use period. So the period of this periodic function is 2 pi. Like this is a periodic function that we sit in, right? Every single day, weekends excluded, we come to first period. And what would be the period? How long does it take for us to come back to first period? 24 hours, right? So the period of this class is 24 hours. Every 24 hours we meet. The period of the sine function is 2 pi, which is one rotation. Makes sense, right? So every 2 pi, this graph repeats itself, all right? So here's what it looks like if you want to unwrap it. This is just another diagram I got off the internet. I think y'all can pretty much understand what we did. All right, now I only used the pi 6 angles to kind of show that it increases at an increasing rate so that we knew to connect the graph with a curve instead of straight lines. Okay, But if we come down here, let's highlight this. Highlight this from 0 to 2 pi. Highlight it from 0 to 2 pi over and over again. This is called from 0 to 2 pi. From 0 to 2 pi, we have what we call one cycle of sine of x. One cycle of sine of x. Okay? So every length of the period, one length of the period, one length of the period is called a cycle. Now, this is also a wave function, as I already mentioned. If you've ever seen an oscilloscope reading in your science class, an oscilloscope measures sound waves. Like as I'm talking right now, my voice is traveling through the air to your ear, and it's traveling in a sound wave which resembles a modified sine function. Okay? Audio waves travel through air in sine waves like this. You can measure the period of a wave function in two ways. You could measure it by the wavelength. How high is it from crest to crest and trough to trough, which is another name for the period. Or you can measure it by the reciprocal of the period, which is called the frequency, right? And what an oscilloscope does is it measures the frequency of the graph, which is how long it takes for it. It takes like a single second, and it counts how many waves pass through there in a single second. Whereas the period or the wavelength measures how long it takes to do a single period. Okay, and we call those cycles. So how many cycles did we see up here? 1, 2, 3, 4. We saw 4 full cycles up here. 4 cycles. Okay, we saw 4 cycles. 4 complete cycles. Down here, how many cycles do we see? I see 1. Let's see if we can highlight the next one. The next one is going to be from 2 pi to 4 pi. So we see two and a little bit more, right? 2 and a little bit more. We see another half cycle over here. Here's a half of a cycle right there. We see the bottom lobe only. That's a half cycle. So we see like 2.5 plus a little bit more, right? So I'm just gonna say that this is 2.5-ish cycles, right? So the period is the length of one cycle. The period is the length of one cycle. The period is the length of one cycle. Okay. Now we're going to talk about this function. This is going to become a new parent function. You're going to be expected to graph the sine function from memory, including all of its characteristics. Okay. So to help you remember how to graph the sine function, I came up with this mnemonic years and years and years ago, and I've used it every single year. It's called the Sahala mnemonic. Sahala. I sometimes forget when I'm talking about the sine function to call it the sine function. Sometimes I just call it the Sahala function. So here's how the Sahala function works. The S in Sahala stands for sine. So it helps you remember that we're talking about the sine function. If we start at x equals 0, we're starting on the x-axis, okay? We're starting on the x-axis. The x-axis runs right through the middle of this wave function, and it bisects it vertically. You see that? We actually call this the sinusoidal function. Let's write that down there. The sinusoidal function runs through the midpoint. It runs through the midpoint. We'll say midpoint vertically. So before we shift this around, we will be shifting it around. It's the x-axis, okay? So we call that an axis point. So we have an axis point. Where do we go from the axis point? That's the A in Sahala. Then we hit a what? A high point. That's the H in Sahala. And then it comes back down to a what? An axis point. And then it heads to a where? To a low function. And to complete one cycle, it finishes up back on the axis. You see that? So Sahala means sine goes axis high, axis low, axis. And that's how you get one cycle. These values right here, these are what I call the critical values. They're the critical values, the A, H, A, L, and A. You need 5 of them. You need 5 critical values for one cycle. You need 5 critical values for one cycle. So the Sahala method tells you where to put those critical values to create one cycle. Okay? So we call that the Sahala method. The period, of course, is 2 pi. That's once around the unit circle. Now in science, you always measure the period as wavelength from crest to crest, which is high to high, or trough to trough, which is low to low. You can do that, but you can also measure it from a place where the graph repeats. Okay, so we start on the axis and we go up. So axis high, and then we hit the axis again, but it's going low. And over here, we're on the axis going high again. So that's the period right there. From the axis going up to the next time we're on the axis going up, the period is 2 pi. All right, let's go ahead and talk about a couple of characteristics real quickly here. What would the domain of this function be? All real numbers. Yeah. All real angles. Remember, these represent angles. All real angles. There is not a single angle in the whole wide world that doesn't have a sine value attached to it. Did you know that? Every angle has a sine value. What's the range of this function? Yeah, we'll do y epsilon, -1 inclusive to 1 inclusive. You're never going to have a sine ratio whose magnitude is bigger than 1. You're never going to have a sine ratio whose magnitude is bigger than 1. Does that make sense based on the definition in terms of x, y, and r? It should, because remember, sine is y to r, isn't it? And y is a short side, and r is the what? It's the hypotenuse, which is the biggest side, long side. So is it possible to have a small number over a big number and have that ratio be bigger than 1, magnitude-wise? No. If you have a small number over a big number, you're going to have a ratio that's between 0 and 1. Now, why can they be negative? Because we rotate into quadrants 3 and 4. But the magnitude, the absolute value, the size of the sine ratio is always going to be between 0 and 1 or 0 and -1 because we're measuring the short side to the long side. That's very, very important. Okay? So it just continues to oscillate forever and ever. That's another word, oscillate. You know what oscillate means? Oscillate means to go back and forth between two values. This wave function, this periodic wave function known as sine of x, just oscillates harmlessly between 1 and -1, 1 and -1, 1 and -1, 1 and -1. And we do it in quarter cycle intervals, okay? Let me talk about that real quickly here. The Sahala method counts in quarter cycle intervals. Quarter cycle intervals. So from 0 to pi halves, that's a quarter of the cycle. From pi halves to pi, that's another quarter of the cycle. From pi to 3 pi halves, that's another quarter of a cycle. And from 3 pi halves to 2 pi, that's another quarter of the cycle. It takes 4 quarters to make one whole, doesn't it? So the Sahala method, the critical values, gives you your quarter cycle counting interval. Okay? Pretty cool. There's one last thing I want to look at characteristic-wise. We know the domain is all real numbers. We know the range is -1 to 1. Let's look at symmetry here. Remember when we talk about symmetry, we're talking about 2 types of symmetry, right? Even versus odd. Even versus odd. What type of symmetry does an even function have? Y-axis symmetry. Does the graph of sine of x have y-axis symmetry? That means, can you fold this graph on the y-axis and have it coincide with itself? I don't see that, do you? If you fold it on the y-axis, the high and the low don't match up, right? So what was the other symmetry? Odd function, right? What does an odd function have? Not x-axis. It's the rotational one. We called it origin. Thank you. Odd means origin. Remember, they both start with O. Odd is origin. That's the rotational symmetry. Does this function have rotational symmetry? If you put your finger down at the origin and turn your iPad upside down 180 degrees. Y'all can do that at your desk. Put your finger down at the origin and turn your iPad upside down 180 degrees. Does it match when you turn it upside down 180 degrees? It sure, yeah, assuming your screen doesn't rotate, right? It does. It has rotational symmetry. So it's an odd function. This is an odd function, It has origin, which we'll put rotational here to remind you. It's rotational symmetry. Now, remember the the implication of that. It means that sine of negative x is equal to negative sine of positive x. That's the definition of an odd function. F of negative x equals the opposite of f of positive x. That's a very important thing to consider when we start doing transformations. The fact that sine is an odd function. Sine of a negative angle is the opposite of sine of a positive angle. Let's see if that works. Let's go over here to negative pi halves. What's sine of negative pi halves based upon this graph? Sine of negative pi halves is -1, right? That should be the opposite of sine of positive pi halves. What's sine of positive pi halves? 1. And what's the opposite of 1? -1. So it works, right? Opposite inputs have opposite outputs. That's another way to say odd function. Opposite inputs have opposite outputs. All right, are you comfortable with the graph of sine of x so far? Sahala. Axis high, axis low, axis. We talked about it. Domain is all real numbers. Range is -1 to 1 inclusive. One cycle has a length of 2 pi. We call it the period. Yeah, that's good for now. All right, so guess what we're going to do? Now that we have the graph of sine of x cataloged in our brain as a parent function, just like x squared is a parent function, square root of x is a parent function, 1 over x is a parent function, e to the x is a parent function, natural log of x is a parent function. Welcome to the club, Sahala, right? Welcome to the club, sine of x. In fact, let's do this. If you ever see sine of x, here's what you should be able to do very quickly. Hang in there, Lawson. Okay? You should be able to say, okay, I'm going to come up here to 1. I'm going to come down here to -1. I'm going to come over here to 2 pi. I'm going to bisect it to get pi. I'm going to bisect it to get pi halves. And then I'm going to bisect the next region and call it 3 pi halves. And then, of course, I got 0. Okay, so now I'm going to graph sine. So I'm going to graph Sahala. And here we go. It's axis high, axis low, axis. And then I connect the dots in quarter cycle intervals. And I can continue on if I need to, right? There it is. There's one cycle of sine. One cycle of sine. You should be able to sketch that graph like I just did very quickly from memory. And if we need more critical values, watch this. If I need more critical values, I'll just keep this spacing right here, which is your quarter cycle. I'll just kind of keep it the same. I'll just kind of eyeball it. And we're counting by what? Our quarter cycle intervals count by what number? What's a quarter of 2 pi? We're counting by 90 degrees, which is every quadrantal angle, aren't we? So it's pi halves. We're counting by pi halves. So 0, 1 pi halves, 2 pi halves is pi, right? 3 pi halves, 4 pi halves is 2 pi. What would come next? 5 pi halves, and then 6 pi halves becomes what? 3 pi. And then we have 7 pi halves, and then we'd have 8 pi halves, which would be what? 4 pi. So if I needed to add more values, I would just keep counting by quarter cycles, which is pi halves, and then I can put my dots. The pattern repeats. Now it's high, axis, low, axis, right? And there's my second cycle, and I have the x values labeled. If I needed to go into negative land, I could do that as well, just by counting by negative pi halves. All right, here's the standard transformation form. I'm just going to introduce this to you today. This is the same standard transformation form that works for every function. We can multiply out front by a. That's going to affect the graph vertically. That's your vertical dilation factor. If a is negative, we reflect it over the x-axis. B is your horizontal dilation factor. It's opposite of what it appears. It's also your y-axis reflection. Then you have your shifts. C is your horizontal shift, which we're going to call phase shift, because it's a wave graph. We call it a phase shift. And then your plus D is your vertical shift, which changes the horizontal sinusoidal axis. Okay. So tomorrow what we're going to do is we're going to start sketching. Well, we'll learn about cosine first. And once we learn about cosine, we'll start sketching transformations of sine and cosine. Question, Brady. The quiz is 10 questions tomorrow, all sine and cosine, yes. All sine and cosine.